class, today we're going to discuss rate of reactions. So what is rate of reactions? So actually there are a lot of chemical reactions happen around our surroundings, and some are fast and some are slow. So what is an example of fast reaction? Such as explosion. And the slow reaction we have rusting of the news and also the food decay. So rate of reaction can be defined as change in the quantity of reactant or product over the time taken for the change to occur. So this is an experiment of magnesium ribbon dissolved in the dilute acid in order to produce a hydrogen gas. So based on this experiment, we can calculate the rate of reactions by identify the change of magnesium ribbon, the change of the mass of magnesium ribbon over the time taken, or we can also measure the volume of hydrogen gas released over the time taken. So let's say I have a reaction which is from reactant A to product B. So if we are drawing a concentration graph, okay, a concentration of product and reactant against time graph, okay, so we will get the concentration of reactant will decrease and the concentration of the product B will increase. So the rate of reaction can be written as rate is equal to the change of reactant A over the time taken. So you can see there's a negative sign. There's negative sign which represent that the reactant is decreasing. And we can also write as rate is equal to positive delta concentration of product B over delta T. So the delta is referring, the symbol delta here is referring to the change. So I can say change of product B over change of time. And you can see there's a positive symbol which represents that product is increasing. And how about the unit? So the unit will be the unit of concentration over time. So concentration, the unit can be in mole per volume. So we have the unit is equal to mole per liter per second, or mole per dm cube per second, or we can also use the M big capital to represent the concentration. So big capital M per second. And next one, instantaneous rate of reaction. So what is instantaneous rate of reaction? Instantaneous rate of reaction is a rate at a specific time during a reaction. So for example, like let's say there's some cars, okay, driving on the highway, and there's a speed track which is installed by the police. So the car is driving at a random speed, and then during the speed track, okay, the car was caught driving at 150 km per hour. So the speed recorded, okay, at that moment is equal to our instantaneous rate of reaction. So instantaneous rate of reaction is referred to the rate of reaction at a particular instant. So on the graph, okay, this is a graph of a reactant C4H9Cl. So if we want to calculate the instantaneous rate at 600 seconds, okay, at if you want to calculate the instantaneous rate when the time is equal to 600 seconds, so what we're going to do is, you're going at the 600 second, you're going to draw a straight line cutting through the time is equal to 600 seconds. Okay, so based on the slope of the line to the curve at the 600 second, okay, so you got the gradient, so the instantaneous rate is equal to the gradient. And the initial rate is at when our time is equal to 0, means that when you are initially, okay, you will start the initial rate when you start mixing the reactants. So it will be determined by the time of the line tangent to the curve when t is equal to 0. Okay, so differential rate equations is used to show the relationship between the rate of disappearance of reactants and the formation of products. So for example, I have a reaction which is 2A will produce 1B. So this means 2 mole of reactant A will disappear when I have 1 mole of product B formed. So the differential rate of equation can be written as rate is equal to 1 over 2 change of reactant A over change of time. So the 1 over 2, okay, the 1 over 2 is actually coming from the coefficient in the reaction. Okay, it's coming from the coefficient in the reaction. And I can write rate is equal to positive change of product B over time. So you can see here, okay, product B, okay, there's 1 more product B form. So you need to write the fractions in the product B. And negative and positive is used to show whether it's a substance increasing or decreasing. So positive is increasing and negative is decreasing. So based on the equation above, how can we write the differential rate equation? So rate is equal to negative 1 over A, change of concentration A over T is equal to negative 1 over B, change of concentration B over time, and equal to positive 1 over C, change of concentration of C over time, and also equal to positive 1 over D, change of concentration D over change of time. So you can see there's a negative symbol showing that reactant is decreasing, and there is positive symbol showing that the product is increasing. And the 1 over A, 1 over B, 1 over C, and 1 over D, this value is taken from the stoichiometric coefficient. It's taken from the stoichiometric coefficient from the equation. So these are the general differential rate equation. So let's look at another example. Hydrogen gas react with iodine gas to produce 2 mole of hydrogen iodide. So the differential rate law will be equal to negative change of hydrogen gas over time is equal to negative change of iodine gas over time, and positive 1 over 2 change of hydrogen iodide over time. So there's no the stoichiometry for stoichiometric coefficient for hydrogen gas and iodine gas is 1. Okay, so you can see here, we don't need to write as 1. Okay, because negative 1 over 1 is also equal to 1. And for hydrogen iodide, it will be positive 1 over 2. So next we're going to see calculations, okay, involving differential rate equation. So based on the questions, hydrogen sulfide burn in oxygen to form sulfur dioxide and water. And a balanced equation is given. So the question said, if sulfur dioxide is formed at a rate of 0.3 mole per liter per second, what are the rate of disappearance of oxygen gas? Okay, so they give you the rate of formation of sulfur dioxide and they ask to find the rate of disappearance of oxygen. So based on these questions, the first thing you need to do is to write the differential rate equation. So rate is equal to negative 1 over 2 change of hydrogen sulfide over time, negative 1 over 3 change of oxygen gas over change of time, positive 1 over 2 change of sulfur dioxide over change of time, equal to positive 1 over 2 change of water over change of time. So based on the differential equations, okay, the targeted question is rate of disappearance of oxygen gas when there is a formation of sulfur dioxide. So we're going to use this to calculate the rate of disappearance of oxygen gas based on the information given. So you substitute the value of 0.3 into the rate of formation of sulfur dioxide gas. So we can find the rate of disappearance of oxygen gas is equal to 1 over 2 multiplied by 0.3 mole per liter per second multiplied by 3. So the 3 here is coming when you rearrange the 1 over 3 fraction. Okay, so 1 over 3, when you rearrange to your right side, it will become multiplied by 3. So when we are doing the calculation, we can ignore the symbol negative and positive because it is to show whether the reactant or product is increasing or decreasing. So we can ignore when we are doing the calculation. So the rate of disappearance of oxygen gas is equal to 0.45 mole per liter per second. If you like my videos, please like, share and subscribe to Madam YY channel. Thank you.